Generative AI requires massive computing power, but a physical hardware constraint is currently setting the pace for how fast these systems can actually evolve. Inside an AI server, two components do the heavy lifting: the processor, often a graphics processing unit, or GPU, which acts as the brain, and the dynamic random access memory, or DRAM, which serves as the library where information is stored. Modern AI processors operate at blistering speeds, yet they often sit idle for long periods. They are forced to wait for traditional memory to locate and deliver the data they need to keep working. Building a faster processor is of little use if the system cannot deliver data to it quickly enough to keep it occupied. To understand why older memory systems struggle, imagine traditional dynamic random access memory, or DRAM, as a sprawling single-story house. When the processor needs information, the data has to travel from this house down a narrow one-lane road, which engineers call a data bus. AI models require moving gigabytes of data every fraction of a second, and trying to force that much information down a single-lane road creates an immediate traffic jam. Simply adding more houses to the circuit board takes up too much physical space and consumes excessive power, signaling that traditional 2D architecture has reached its limit. High bandwidth memory, or HBM, was designed to solve this data shortage by changing the physical layout of the chips. The most significant change is the move toward verticality. Instead of spreading memory chips out flat across the board, engineers stack them straight up like a high-rise building. This stack starts with a base die. On top, engineers stack core dies, reaching up to 16 floors high. The base die acts as the lobby, managing the physical layer, or PHY. This circuitry handles the electrical signals connecting the memory to the system. This vertical design packs massive storage capacity into a very small footprint, which solves the space constraints on the circuit board. Even with a tall building, you still face a bottleneck if all the residents have to leave through a single small exit. HBM solves this with a wide interface architecture. It replaces that old one-lane road with a massive 1,024-lane superhighway. Physically, this highway uses thousands of microscopic solder bumps on the bottom of the memory stack. Each colored box in this grid represents a dedicated connection. These connections are divided into independent channels, allowing different data streams to flow simultaneously without waiting. This massive number of parallel lanes is what high bandwidth actually looks like in practice. Managing traffic across 1,000 lanes at 6,400 megabits per second requires incredible precision to prevent data errors. Megabits stands for megabits per second, which measures how many millions of data bits are transferred every second. To maintain this speed, HBM uses double data rate, or DDR. DDR is a method that allows data to be sent on both the rising and falling edges of a clock signal, effectively doubling the transfer rate. The memory also performs a process called training, where it constantly self-calibrates to keep every single lane perfectly synchronized. This combination of a wide physical path and precise timing ensures the processor never has to pause while waiting for its next piece of information. The final challenge is the physical distance the data must travel between the memory and the processor. Unlike traditional RAM, which sits in slots across the motherboard, HBM is built onto the same piece of silicon as the GPU. This tightly coupled layout places them mere millimeters apart. Reducing this distance allows the system to move data almost instantly while using significantly less electrical power. By combining the vertical skyscraper design, the 1,000-lane highway, and the near-zero distance commute, HBM removes the barriers to high-speed computing. This specific architecture provides the necessary data throughput to make massive AI models like ChatGPT a reality. The future of artificial intelligence depends on more than just code. It relies on the physical highways we build to feed it. If you want to see more hardware deep dives, subscribe and let us know what we should cover next.